We are studying voltaic cells. In the previous video, we built a zinc copper cell, and we can represent that build in the following manner. We say we built a zinc copper cell or voltaic cell, or so we can say the zinc copper galvanic cell. So let's summarize. Electrochemical cells can be of two types. One, which is the voltaic cells, and the other one, which is the electrolytical or electrolytic cells. In one hand, voltaic cells uses spontaneous redox reaction to produce electricity. In other words, the flow of electrons through a wire. For the electrolytic cells, occurs the opposite. We use electricity to drive a non-spontaneous redox reaction. So you see, voltaic cells produce energy, produces electricity, whereas electrolytic cells they consume energy as form of electricity. And we built a zinc copper voltaic cell. Let's review how we did that. You've been asked to build a zinc copper voltaic cell. And you need to find the potential for that cell. That's the question. What is the potential, standard potential for that cell? What cell? Zinc copper cell. So how do we do that? We use a standard electropotentials to find the half reactions, one half reaction for copper and one half reaction for zinc. And we just found from the table that is also posted on the Blackboard, one half reaction. For the copper, we found zinc solid plus 2 electrons in equilibrium to form zinc metal. And this half reaction has a potential EMF or electromotive force equals to negative 0.76 volts. And we found the equation for the copper for that cell using the same table, the standard electropotential, and we found that copper solid plus 2 electrons are in equilibrium with, this is, oh, hold on, wait a minute. I just realized I messed up. We have copper zinc ions 2 plus aqueous and copper ions 2 plus aqueous, plus 2 electrons to form the copper metal. And the table shows us that that particular half reaction has an standard electropotential of plus 0.34 volts. We learned that the value that has the most negative value will undergo oxidation Therefore, that will represent the anode of our voltaic cell. Therefore, the copper will undergo reduction and will represent the cathode of our voltaic cell. So the one with the larger reduction potential will gain electrons and undergo reduction. That's going to be copper, copper 2 plus. And the one with the lower reduction potential will give up electrons and undergo oxidation. That's going to be the zinc. But notice, again, as I mentioned it before, the table is written as a reduction. That's standardized. All of them are written as reduction, gaining of electrons. We need to find for our particular build-up which one is being oxidized and which one is being reduced. We just found here by comparing these two numbers, looking at the charges of the numbers, the signs of the numbers, the copper will undergo reduction, therefore it's going to be the cathode, and the zinc is going to do oxidation. So that means we need to reverse this reaction. Again, when we compare these two, we say this is going to be oxidation, but the equation, as we took it from the table, directly from the table, is showing reduction. We need to reverse. So let's reverse that here. So it's going to be zinc, solid, and it will lose electrons to form zinc 2 plus, aqueous plus 2 electrons. So the potential of the cell, standard potential of the cell, since we reverse it, now is plus 0.76 volts. And this is the oxidation. The anode, at the anode. Now we can add the two equations to find the potential of the cell. We add equation 1 and equation 2. The equation 1 is the reduction half reaction, and equation 2 is the oxidation half reaction. Again, we reverse that because when we compare these two numbers, we realized that zinc, by having less or most negative potential will undergo under oxidation. So let's add these two equations. Notice that in this case, we have number of electrons gain the same as number of electrons lose. And that's what we want. We want a balance of electrons, gain and lose. Yeah. This one is losing 2 electrons and this one is gaining 2 electrons. So we need to have, every time you build up any voltaic cell, you work the equations this way. You want to make sure the number of electrons gained are exactly same as number of electrons lost. In this case, we say that N for this reaction is 2, because 2 electrons are being involved on these singular steps. If your equations showing different electrons because you have different reactions there, so you want to multiply by a number in order to balance that. Let's say you have 2 and 3 here, 2 here, 3 here. How do you balance? You multiply the first equation by 3. 3 times 2 equals 6. Everything multiplied by 3. 3 times this, 3 times this, 3 times this, except the number. You don't, in this case, in another reactions, we did it, you multiply by, for example, the value of enthalpies, but not this case. That number will not multiply that. And you multiply this by 2. 2 times this, 2 times this, 2 times, I said, in the case you have 3 here, so you will have 6. So you have the equal number. In our case, this real case, we don't have to do that because we have equal number of electrons, and we say N equals, for this case, N equals 2. N is the number of electrons involved in the process. And we cancel because they are gained and lost at the same time with the exact amount. So now we can add these two equations. In this side, we have copper, 2 plus aqueous, here, plus zinc, solid. And on the other side, we have copper, solid, plus zinc, 2 plus aqueous. And the standard potential of the cell, when you add these two numbers, you got 1.10. You see, two different ways to do it. Previously, I showed you using the equation. You use this equation, you don't have to reverse anything, just plug the numbers as you find it on the table. And you got 1.10 volts. That's the standard potential for the cell. However, eventually you will have to do this because you need to find which one is the oxidation. And once you identify the oxidation half reaction, you need to reverse that from the original one that you found on the table of standard reduction potentials. And you find the potential of the cell, 1.10 volts. There are different ways to write these, different notations. And I'm going to show you the standard notation. So you will understand every time you read electrochemical reactions, problems, you should be able to translate that into human language, so you will understand. The first, let's learn a simple way to write this information. For example, for the oxidation, you can write this information also as, for example, you want to say the standard potential for the oxidation of zinc 2 plus to zinc metal equals negative 0.76 volts. For the second half reaction, you say the potential for the reduction of copper 2 plus to copper is 0.34 volts. That's how you get it from the table. However, since we know now that zinc is going to be oxidized, we should write it zinc metal to zinc 2 plus, that's oxidation. And copper from 2 plus to copper 0, that's reduction. So that's how will you represent the process. But remember, you know that only, once you know, identify your two electrodes, find the values on the standard electropotential, and the most negative is the one that is going to do oxidation, and you need to reverse that equation. All right, the other one is called the standard cell notation or line notation. What is that? Cell notation. It is also called the line notation to represent what is happening in the cell. And that will represent also the equation. This is the overall equation. So let me show you using a graph. Again, we have two beakers. Let me do it a different way. I'm going to draw something different. So you will see there are different ways to do this. In the lab demo, I mentioned it. Professor Gorbenko used paper to build out the cells. In this setup, I have the same two cells, and between the two cells, I have a porous material. Usually it's made of ceramic, very porous ceramic material. that will allow the exchange of ions between the two cells. So on this first cell, we're going to place our zinc electrode, and we just learned that the zinc is going to do oxidation. Therefore, the zinc is going to be our anode. On the other cell, we're going to place the copper metal. This is metal. And therefore, we just found this is plus. It's going to do the reduction. Therefore, it's going to be our cathode. This is going to be our anode. So the zinc will lose electrons, and the electrons will stay here, and they need to go somewhere. That's why we need to connect these two electrodes using a wire, but in between we can place a voltmeter to measure the potential difference between these two. You can also put here a light bulb. So you can actually make the electrons to do work. Electrons will flow from the oxidation, from the anode to the cathode. And you can put these electrons to work. They can do a work for you. They can move a little motor, and this is going to be a direct current, a DC current. So they can move a little DC motor, electrical motor, or light up a light bulb. I just place here a voltmeter, and you should observe the production of 1.10 volts under standard conditions. Those are ideal conditions. I mentioned it before, it's not going to happen for the reasons I mentioned it. There's no need to do salt bridge because we already had the porous material, so the ions will move from one side to another side. Zinc ions, this electron is going to produce zinc 2 plus ions, and they will move that direction. Nitrate ions will move the other direction to balance charges here, and then the reaction will work. And I just forgot to mention that the electrons are immersed in a solutions containing the metal ions. On zinc, zinc ions. For the copper, copper ions. We can represent this apparatus using something that we call the standard cell notation. And that goes this way. Always start with the oxidation. So I'm going to represent oxidation first here. Oxidation. What is happening here at the oxidation cell? And I'm going to represent my salt bridge using these parallel lines. These parallel lines here these two bars represents the salt bridge and will separate the two phases. We have two phases here, aqueous and aqueous, right? Between these two cells, we have aqueous phase and aqueous phase. So this double bar will represent that in the cell. Salt bridge, and this is the two phases. And on the other side, I represent the reduction. What's happening at the reduction cell. So by convention, always you start with oxidation. So that's why it's very important you identify which one is going to be oxidized and which one is going to be reduced. So let's start. The standard cell notation, you start with the metal, which is the zinc that is being oxidized. And the interface with the solution containing these ions. What ions are those? Zinc 2 plus, aqueous, and this is solid. How do you separate this with the other cell? Using the double bar that represents the solvent. So on the other side of the cell, what we have? Solution. And what metal is in the solution? Copper. 2 plus ions, aqueous. And the interface is with copper, metal. And this is what we call the standard cell notation. And we, in front of this, we write the standard potential of that cell, the whole cell, is 1.10 volts because we just calculated it. This is how you represent, sorry for that, represent the cell notation for that particular cell. So again, always start with the oxidation, the metal. This is the phase, one line. The interface with the solution containing ions of the metal. Then the salt bridge, the double bar. Have the solution containing ions of the metal. And here represents with another bar the separation, the interface between this metal and the solution. We have interface there, solid and aqueous. That's what we're showing here. And this battery has enough potential electrical energy to push electrons through the wire to do the work. All right. What about if you don't have standard molar concentrations? What about if you have a different concentrations on the solutions? Let's suppose you have a solution that is not standard. What is the standard concentration for these cells? Is 1 molar. What about you have concentration that is not standard? Let's say you have 0.001 molar solution of zinc 2 plus. So you write that cell this way. Zinc, solid, zinc 2 plus, and you write the concentration here, 0.001 molar. This is the salt bridge. On the other side, let's say you have a 0.1 molar of copper 2 plus. Copper 2 plus, 0.1 molar. And the interface with copper solid. Do you think that cell is going to produce the same amount of energy? Probably not, right? You get 1.10 molar, sorry, 1.10 volts if you use 1 molar solution of this and 1 molar solution of this, which is the standard. And that's what we call this notation, the standard cell notation. You notice that now we have different concentrations, therefore, we cannot call it standard. I have to go back and delete that standard there. Sorry. It's not standard. We are using different concentrations. This is a standard because we use 1 molar and 1 molar. We use 1 atmosphere pressure, and we use standard temperature. If you change the concentration, now it's not going to be standard. So how do you calculate the potential of the cell using this concentration? We are going to use something that is called the Nernst equation. Nernst equation will help us to calculate that. It's called Nernst equation. Oh, I missed, let me see. Nernst equation. And I'll show you that later on. Let's find also what is the relationship between this potential difference and free energy. We just learned that the maximum electrical energy we can get from that cell, which is the electromotive force, equals negative maximum work produced over charge, where Q, the charge, equals NF. What is F? F and it's Faraday's constant. Faraday, also a genius who was working with these cells, he found a constant. It's the number of electrons transferred, which is N, number of electrons transferred, times Faraday's constant. He found that to be 96,485 coulombs per mole. So that's 1 mole of electrons move a charge of 96,485 coulombs. And I posted a video about Faraday's life and Faraday's experiments on the Blackboard. Very interesting. So we rearrange this term from here. We found that Q charge times, let's move over here, E max equals maximum work. Energy transferred as a maximum work. What is the how do we measure the maximum available work for a chemical reaction? We call that delta G. So we can say that, and what is Q? Q equals NF. So NF times E max equals delta G. And since E max equals the standard potential of the cell, then delta G for a system to be spontaneous has to be negative NF standard potential of the cell. That's the relationship between potential of the cell and the free energy. So remember, for the system to be spontaneous, delta G has to be negative. And if we can remember the definition we have from the previous chapter, delta G of non-standard process equals delta G standard of the reaction plus RT natural log of Q. Therefore, delta G under non-standard conditions will be, this is standard, negative N F potential of the cell under non-standard conditions. That's why I'm not putting the symbol here for standard. Equals delta G standard, which is negative N F E standard of the cell. That's potential of the cell plus RT natural log of Q. So notice that NF is constant on both sides. Remember, N is the number of electrons participating in the chemical process for this reaction, and we found that N was 2 electrons. Remember from here? 2 electrons. So this is, from here you obtain how many electrons are participating in the process. After you balance the 2 equations. So these 2 numbers are constants. Therefore, E of the cell under non-standard conditions equals standard potential of the cell plus RT natural log of Q. So what is Q? Q, as you remember, is the reaction quotient. We learned on equilibrium chapter. For the previous, for our system, what is Q? So we need to find the overall. This is the overall equation we found. From here, we can find the Q, the reaction quotient for that case. So what will be Q for that? This is the overall. After you add the two half reactions. And remember, in order to do that, you need to reverse the reaction that is doing oxidation, showing actual oxidation. On this side, how do you know it's showing oxidation? Because in this part of the equation, reactive, you're seeing electrons. Oh, sorry, here. This part of the reaction is producing electrons, is losing electrons, going away. This is gaining electrons. On this part is reduction because it's gaining electrons. Electrons are on the reactive. If electrons are on the product side of the equation, then, so you have a equation written as oxidation. This equation here is written as reduction. So if you reverse it, it's going to be the opposite. So Q will be, what do we have here? Concentration of zinc 2+. Remember, this is solid, is now included into the Q expression, into the mass action law, over what do we have over there? AQS only, no solid, no pure solid, no pure liquids. Copper 2+. So that's our reaction quotient. And what is the reaction quotient? Whatever you have initially. So for this case, I'm showing we have initial concentrations of copper 2+ and zinc 2+. So with those numbers, you can find the reaction quotient and find the potential of the cell using different concentrations. So let me rewrite that here again. Reaction quotient will be, what was that? Zinc 2+. Yeah. Concentration of zinc 2+ AQS over concentration of copper 2+ AQS. And that's your Q here, you can replace that. So what is R? R also is a constant, which is 8.1 joules per Kelvin mole. We know the potential of the cell. Temperature is the standard temperature. If temperature is not given, you can use the standard temperature and we can find the potential of the cell. So potential of the cell under non-standard condition will be standard potential of the cell we just found, which is 1.10 volts plus 8.314 joules per Kelvin mole, Kelvin -1 mole, -1, times, let's use standard temperature, 298 Kelvin, times natural log of what is the concentration of zinc 2 plus? We said 0.001, I believe, 0.001. 0.001, and the concentration of copper 2 plus was 0.1. And you solve this equation and you find the potential of the cell under non-standard conditions. But we have a situation here. This, when you're using these initial concentrations, and the battery will start producing that voltage. And over time, it's consuming the material, and concentration will start to change, right? Because we have an equilibrium here. And the reaction will shift towards the equilibrium, either to the right or to the left, depending if we compare these initial concentrations with the equilibrium constant, we'll know if the reaction is shifting to the right or to the left. So over the time, the reaction is producing voltage, but also this reaction here is shifting, exchanging ions, concentrations of ions change over the time until what? Guess what's going to happen? The system will become at equilibrium eventually. And what will happen? What will happen at equilibrium? So at the equilibrium, what is the meaning of equilibrium? Delta G standard of the reaction equals what? 0. Means what? You say the battery is what? Is there. It's not producing more voltage. Why? Because the system becomes or reach the equilibrium. So no more potential difference to push those electrons to do the work. Therefore, we plug that into the first equation here, into this one. We say that delta G, let me rewrite that again, delta G, this one here, equals delta G standard plus RT natural log of Q. So we have this one here. If the system becomes at equilibrium, that means Q at equilibrium, Q will become K. and delta G standard will become 0. So delta G will be, this is 0, RT, this is capital T here, absolute temperature, RT natural log of K. So delta G standard equals negative RT hold on, put on the wrong side. Delta G will become 0, and delta G standard will become negative RT natural log of K. And what is this? It's going to be negative N F standard potential of the cell by definition. So the standard potential of the cell at the equilibrium will be RT over NF natural log of K. And we can use this equation to find the value of the equilibrium constant. We take anti-log on both sides, we find the equilibrium constant equals E to the NF E the cell over RT. And this is what we call the Nernst equation. I promise I will show you different ways to calculate the equilibrium constant. And this is another way. All right. So now we learn how to build a voltaic cell, how to write standard cell notation or line notation, how to find potential of the cell, how to find the free energy of the cell. For this particular case, the free energy will be the standard free energy for the cell, which is negative NF standard potential of the cell. Is easy to calculate, which is going to be negative N, for our case, 2 electrons times Faraday's constant, which is 96,485 joules per coulomb, times no, sorry, it's coulombs. The units of Faraday are coulombs. I lost my eraser. For some reason, and I don't like to make a scratch here. I'll try to make this work. Okay, I think I will have to do some scratching here because I lost coulombs. Per mole. Times the potential of the cell, we just calculated to be 1.10 volts. And that's how you find the potential of the cell. And most important, this number has to be negative. And the answer will be in joules per mole. So your potential of the cell has to be always positive. Has to be always positive. What happens if the potential of the cell becomes negative? Once you put two cells together and you do the calculation and find the potential of the cell here to be negative. Always has to be positive for the battery to work, to produce energy. So if for some reason the potential of the cell becomes negative, you are in trouble. Because once you plug that negative here, negative times negative is going to give you positive free energy. Meaning what? The reaction will be not spontaneous, and so the battery won't work. So the two materials you put in together will not produce electricity. You need the potential of the cell to be positive. So when you plug that into here, the free energy will be negative, therefore the reaction will be spontaneous and your battery will work, will produce energy, and you can put it to work.